Hari Om. Today, let us proceed to the topic equipotential surfaces. Now, from the word itself, you might be able to guess the meaning of this. Equi means equal, and potential, as you already know, is given by V. So, surfaces. What are these? These are the surfaces along which the potential remains same. For example, suppose we have a positive source charge which is situated at this point. So suppose we have a positive charge of plus Q which is situated at this point. Now due to this charge, what is the potential? How much did we derive? Potential is given by K Q by R. Alright. Now suppose I draw a sphere, a spherical surface around it. By sphere I mean the radius is same. In a sphere, radius remains same. So if I take a point over here, if I take a point on the surface of that sphere, then what will be the potential here? So potential will be K. What is the charge? Q. And distance between charge and point is R, radius. Similarly, if I take a point over here, what will be the potential? K. Charge is Q and distance is R. As you can see, both the points have the same potential. Similarly, if I take a point here, what will be the potential? It will be K into charge by R. So, if you take any point on this surface, the potential will be same. Such a surface on which potential is same due to a given charge is called as equipotential surfaces. Suppose we take another spherical surface with some other radius r dash. On the second surface also, no matter how many points you take, the potential will be K charge by distance. Here the distance becomes r dash. So all the points on this surface form a given equipotential surface. Similarly, on all the points on this surface will form a different equipotential surface. Similarly, if we take a surface nearby with some other radius r double dash, this will also be an equipotential surface. So for a given point charge, the equipotential surfaces are spherical in shape. Now if we take a parallel electric field, if we have a region in which there are parallel electric field, so or we can say this as uniform electric field. Uniform electric field. So in this case, what will be the equipotential surface? Here the equipotential surface will be sheets. This will be an equipotential surface. This sheet is on a surface. So no matter which point you choose from this sheet, the potential will be same. Here also the potential will be same. Here also the potential will be same. So here equipotential surfaces are the form of plane sheets. But here they were in the form of spherical surfaces. So to remind once again, these are the surfaces on which potential of a given charge distribution is equal at all the points. Alright. Now if we take a dipole consists of negative Q and positive Q separated by some distance. So negative charge, positive charge separated by some distance. So what will be the equipotential surfaces due to this configuration? So if you remember, while deriving the potential due to a dipole, we saw that the potential along this line is 0. That is, if you take any point on the equatorial axis, then the potential at that point will be 0. So at this line, potential is 0. So all the points of this line or this plane, which is like a sheet like this, form an equipotential surface. Similarly, for a dipole, there are some other equipotential surfaces also, which look like this. These are all equipotential surfaces for a dipole. They depend on the type of charge distribution. This is our negative charge, positive charge. separated by some distance, and these are all surfaces, equipotential surfaces. These diagrams you can find in a better way in your books. This is a main equipotential surface at which potential is 0. Alright? Okay, so remember that every point on a given surface, so suppose we take this surface, so all the points on this surface have the same potential. Similarly, all the points on this surface will have the same potential. All the surface on this line surface have the potential 0. Such are called as equipotential surfaces. Now let us proceed to the properties of equipotential surfaces. The first property says that if you want to move a charge, any charge, on a given equipotential surface, then the work done will be 0. Suppose, let us consider that this is an equipotential surface. This is an equipotential surface due to some charge distribution. So potential of this surface is suppose V. That means at this point the potential is V. Here also potential is V. Here also potential is V. So suppose this point is A and this point is B. You want to move a charge from A to B. So suppose you want to move a charge of magnitude Q from A to B. As you know, work done is Q V2 minus V1 or Q into delta V. So this will be Q V2. So potential at the second point is V minus potential at the first point is also V, because this is a equipotential surface. Q into V minus V is 0, so 0. Hence, if you want to move any charge on a given equipotential surface, you don't have to do any work. Okay. Next, coming to the second property, it says that the electric field lines are always perpendicular to the equipotential surfaces. In order to understand this, we have to consider some cases. Suppose this is an equipotential surface of potential V. So let us consider that we are moving a charge Q from A to B. There are 2 points and we want to move the charge Q from A to B. So this is our direction, that is dr vector. R vector represents displacement or position. So this is our dr vector. Now as you know that change in potential is equal to change in electric potential energy per unit charge. So dV is equal to du by q. Now the change in electric potential energy is nothing but change in work done. So work done from moving the charge from A to B is given by dW. So dV is equal to dW by q. Now as you know that electric field is equal to minus of dV by dr. We have already established this relation. Electric field intensity is the negative of potential gradient. So we can write that E dr is equal to minus dV, or seeing the direction of E and dr, we can write this as E dot dr is equal to minus dV. So this will become E dot dr is equal to dW by q. Instead of dV, I am applying E dot dr. I am neglecting the minus symbol by keeping in mind the direction of it. Now since work done for moving a charge on an equipotential surface is 0, as we have seen in the previous property, dW is 0. So E dot dr is 0. Now what does this mean? Dot means E dr cos theta is equal to 0, and as you know electric field cannot be 0, and dr means this displacement, so we are displacing, this is not 0, so cos theta has to be 0. And when is cos theta 0? Cos theta is 0 when theta is 90 degree. So the angle between electric field and dr vector is 90 degree. So similarly, whatever may be the direction of dr, electric field always has to be perpendicular. So electric field will be something in this direction, so that it will be perpendicular to all the displacements in a equipotential surface. Alright. In the next property of equipotential surfaces, suppose we have a region in which there is non-uniform electric field distribution. So as you can see, I am drawing non-parallel lines. So electric field is continuously decreasing or whatever it may be, but it is not uniform. Now in this case, equipotential surfaces are something curved, a bit curved in nature. Now this is a equipotential surface, this is another equipotential surface, this is one more equipotential surface, and so on. Suppose the spacing between these two equipotential surfaces is dr and electric field is E here. So as you know that E is equal to minus of dV by dr. E is minus of dV by dr. Now suppose we concentrate on two different surfaces. Then suppose the potential on this surface is V1, potential on this surface, whole surface is V2. Since this is an equipotential surface, potential on all the points is V1 and here potential on all the points is V2. So the difference between the potential, that is dV, so V2 minus V1 is same for all 2 points. If you take 1 point here and 1 point here, dV is a constant. So here dV is a constant. So this becomes E is equal to some constant by dr. dV is constant. Why dV is constant? Because potential is V2 in all the points of this surface and it is V1 in all the points of this surface. So if you choose 1 point from this surface and another point from this surface, then difference will be V2 minus V1. Here also if you choose any 2 other points, difference is still V2 minus V1. That's why dV is a constant. Now as you can see, electric field is inversely proportional to dr. So in a region where electric field strength is more, so if electric field strength is more, what will become to dr? Dr will be less. And if you remember what was dr? Dr was the spacing between equipotential surfaces. So if equipotential surfaces are nearer to each other, in that region electric field strength is more, or if dr is less, the electric field strength is more. If dr is more, as you can see here, the spacing between two surfaces is more, so electric field strength is less compared to the previous case. As you have already seen, suppose we take a point charge, positive charge, then due to that point charge, our equipotential surfaces will be something like this, and so on. So spheres will be forming. But here you can see near the charge, equipotential surfaces are close apart. So because near the charge electric field strength is high, so their equipotential surfaces are very near to each other. But as we go far apart, the distance between two equipotential surfaces increases. Okay. In the next property of equipotential surfaces, suppose we have a region in which there is non-uniform electric field distribution. So as you can see, I am drawing non-parallel lines. So electric field is continuously decreasing or whatever it may be, but it is not uniform. Now in this case, equipotential surfaces are something curved, a bit curved in nature. Now this is a equipotential surface, this is another equipotential surface, this is one more equipotential surface, and so on. Suppose the spacing between these two equipotential surfaces is dr and electric field is E here. So as you know that E is equal to minus of dV by dr. E is minus of dV by dr. Now suppose we concentrate on two different surfaces. Then suppose the potential on this surface is V1, potential on this whole surface is V2. Since this is an equipotential surface, potential on all the points is V1 and here potential on all the points is V2. So the difference between the potential, that is dV, so V2 minus V1 is same for all 2 points. If you take 1 point here and 1 point here, dV is a constant. So here dV is a constant. So this becomes E is equal to some constant by dr. dV is constant. Why dV is constant? Because potential is V2 in all the points of this surface and it is V1 in all the points of this surface. So if you choose 1 point from this surface and another point from this surface, then difference will be V2 minus V1. Here also if you choose any 2 other points, difference is still V2 minus V1. That's why dV is a constant. Now as you can see, electric field is inversely proportional to dr. So in a region where electric field strength is more, so if electric field strength is more, what will become to dr? Dr will be less. And if you remember what was dr? Dr was the spacing between equipotential surfaces. So if equipotential surfaces are nearer to each other, in that region electric field strength is more, or if dr is less, the electric field strength is more. If dr is more, as you can see here, the spacing between two surfaces is more, so electric field strength is less compared to the previous case. As you have already seen, suppose we take a point charge, positive charge, then due to that point charge, our equipotential surfaces will be something like this, and so on. So spheres will be forming. But here you can see near the charge, equipotential surfaces are close apart. So because near the charge electric field strength is high, so their equipotential surfaces are very near to each other. But as we go far apart, the distance between two equipotential surfaces increases. Okay. Now the fourth property says that two equipotential surfaces cannot intersect each other. Suppose this is one surface, this is another surface, and if both have intersected each other at a point or a line, so at this point, what will be the potential? Suppose the potential due to this surface is V1 and potential due to this equipotential surface is V2. So at this point you are going to have two values of potential. So at A, potential of A will be V1 as well as V2. But potential is a scalar quantity and at a given point there is only one value of potential. So two values of potential is never allowed or do not exist. Hence, two equipotential surfaces cannot intersect each other. This was the last property of equipotential surfaces. So let's stop here today. In the next video, we will proceed to some next part of this lesson. Thank you.